Hi everyone. Today we are starting an introduction lecture on VLSI. First of all, in this I'll show you some old images related to big size computer which used to be there in earlier days. Okay, so you can see here on the screen you have a big this complete structure which you see in an entire room, this entire room that gives in a computer, which is the name it is given, electronic numerical integrator and computer. Okay, which is in 1946 in February it was designed and it was used old. So this complete big room, it is the all the components of vacuum tubes, this is everything is going to be there. The big room size computer, it is going to be there in 1946. Okay, then afterwards it was experiments were made and research were done. Then in 1950s around and after 1946, 1948 and 50s, they introduced a bipolar junction transistor, and at the same time they invented the IC form of the design. But the fabrication of ICs was it going to be very costly when compared to BJT's earlier days before, that is 1960s. So BJT comes into picture and it was used very much in the designs. Later, as the time progresses, machinery, high-end machinery came into picture. In 1960, you can see here you have two images. Okay, this image here you have this diagram which you can see, figure 2 here you have. So in this figure 2 you have a single transistor planar. Okay, this one you have, this is figure 2, a single transistor planar IC which was designed in 1960. Okay, then afterwards research were made, many researchers were given the time and they have designed very complicated integrated circuit. When it comes to later period, you can see here, okay, 1990. Okay, there is a 30 years gap between this single transistor planar IC means integrated circuit. Okay, then it comes to the era of 1990 where you have microprocessor, where the number of transistors in this are going to be in millions of transistors. I'll tell you how the millions of transistors are placed in a single IC of micrometer by micrometer size. Okay, we'll see that. Now I'll write one thing here. The topic we have started is introduction to VLSI, and I have not told what is VLS. I'll tell you. VLSI is all about very large scale integration. Okay, very large scale integration means large number of transistors are fabricated on a single IC. And the meaning of integration here is, for example, if you have an adder, okay, adder circuit, you have a subtractor circuit, you have a multiplier circuit. So these all the adders, subtractors, multipliers, and the other memory, this everything, if they are an individual ICs, okay, the occupied area by these ICs is more. So if you fabricate all these ICs, the work of these individual ICs, that is adder, subtractor, multiplier, and memory, whatever the arithmetic logic unit required, all on a single IC, then it is nothing but large scale integration. okay, where you're going to have lakhs of transistors. That is very old. It is lakhs and millions. I'll show you how it is very old, that lakhs of transistor, and how the lakhs of transistors earlier and now it is in billions of transistors nowadays. It is hundreds of billions of transistors are present on a single IC. That I'll tell you how it is able to fabricate those many number of millions, and now it is in billions of transistors. Okay, so 1960s it was just a single IC, and when it comes to 1990 you have this Motorola 68040 microprocessor. As I said just now, it is millions of transistors. Now if you see here the red line here, as in 2022, okay, 114 billion transistors was a huge number. You know, billion means 100 crores. Billion is 100 crores. 114 billion transistors. Even you can't imagine, that is a big number. So big number of transistors are integrated, and very small size. You can think it as micrometer by micrometer, tens of ones of micrometer the size it is going to be. Then how it is able to have millions of transistors? Mean the size of the transistors, it is going to be in nanometers. 10 to the power of minus 9 meters for a single transistor. Minimum size of a transistor will be nanometers, and here it is given. I'll just read you here. 114 billion transistors in Apple's ARM based dual die M1 ultra system on a chip. Okay, and this is fabricated using, for the fabrication it is TSMC, means Taiwan Semiconductor. Okay, Taiwan Semiconductor is a industry available in Taiwan. So there it is having 5 nanometer semiconductor, that is minimum feature size on a transistor, which is going to be channel length. I'll show you what is channel length, everything. So the size of the transistor comes to nanometers. So on micrometer by micrometer or less than that itself, we can have billions of transistors. 10 to the power of minus 9 around than average it required for a single transistor. Okay, so that's why 114 billion transistors. I'll just tell you how it was done. Okay, so how it used to be done is, if you have consider a newspaper. Okay, you have a newspaper, and the newspaper you're going to have the alphabets. For example, news, it is written news of New Delhi. Okay, news of New Delhi or something it is written. So here you have alphabets. Okay, 4 6 and this 5, it is 11 alphabets are there. Like this, your entire newspaper is filled with some sports news, whatever it is. You have number of alphabets present on a newspaper page or your textbook page, or here itself we have number of alphabets on a page. Okay, these are visible alphabets. Suppose you have the size of these alphabets is very small, it is taken into nanometers. Imagine how many number of transistor can this size, it is very big. Okay, this much bigger, which I am drawing here the rectangular shape, this much bigger IC will not be there, because a chip actually inside it is going to be very small, and which we see, anybody seen the Pentium processor IC, or you have seen the logic gates, OR gate, AND gate, NOR gate, which you have done in third year logic, mean in the lab. Okay, IC size it is going to be in centimeter size. Okay, 2 centimeters, hardly 3 centimeter size. Inside actually you are going to have the chip. Okay, that is black color, what we see is the external one, that is for the safety of the chip which is present inside. Okay, now it is like you have a chocolate and it is covered with a wrapper. Okay, the wrapper is nothing but your black color one, Inside actually you're going to have the chocolate, that is going to be your chip. The chip size is very small when compared to your IC, which we able to see the processor i3, i5, i7, i9. What are the Pentium processor, ARM processors you have? Okay, the size, right? So I think it is clear how, and in a micrometer by micrometer range you're going to have billions of transistors, or millimeter by millimeter size you can have the billions of transistors can be present on millimeter by millimeter size. Okay, hundreds of billions, and millimeter size by millimeter size, right? Next we have, what is the need for these ICs to have to be fabricated? What is the need for these ICs? So now only I have told, if you're going to have a individual adder, subtractor, multiple like this, individual ICs that occupy larger area on the breadboard or PCB wherever we connect. Suppose if you integrate all these on a single IC, where you're going to have the number of transistors increased on an IC, so that is integration improves. Okay, what it improves, the required space area is going to decrease, that is the main advantage. Okay, now next we have size. As I said, the size area, size required, earlier you have 3 ICs. Now all the 3 ICs you are going to integrate it and made as a single IC. Single IC. Okay, right. So that means the size required is going to be reduced. Nowadays everybody wants to have compact size devices. Laptops you want to have compact, phones you want to have compact, very small size. We want to have those. Whenever we go for integration, the size is going to be very less, and speed it is going to increase, because the wiring required to make, earlier when you have 3 individual ICs, the wiring which you have to made is external wiring between these ICs, adders, multipliers, subtractors. Now all these individual chip, inside you're going to have actual chip here, here, and here you're going to have the actual chips. So all these are present on a single IC. Okay, and you're going to have the wiring external, and you're going to have the external pins which we see. Okay, number of wiring, it is not so simple as I have drawn, it is very complicated. Wiring will be there, that we'll study in later classes. So the wiring in between the chips, the size of the wire is very small. It is going to be in micrometers size or nanometer size. So the electrons which need to flow to cover small distance or speed is very high. When it compares to the external wiring where it comes into the centimeter size, so speed obviously is going to increase with respect to size, as well as more number of transistor you have given, the speed of the operation is going to increase. For example, you have the RAMs. Okay, you have 2 GB RAM, 4 GB RAM, 8 GB RAM, some 16 GB, 32 GB RAM. But if you see the size of the IC, it is not increased, only the size of the transistors decreased, and number of transistors on the IC is increased. Number of transistors in IC are increased. So the memory size is increased from 2 GB earlier to now 32 GB, and further you can even design 64 GB RAMs. Size it is going to be same. You can see the cell mobile phones, 2 GB RAM phone, 4 GB, 8 GB, 16 GB. Mobile phone size it is same, but the memory size it is increasing. And ROM if you take 128 MB, 256, sorry, 128 GB, 256 GB like that. But the mobile phone size is almost same. It is not increased. Okay, that is because the size of the transistor is going on decreasing, and power required is also decreases as we integrate here. Single power supply here it is required to connect one single IC. Power requirement is going to be decreased, and the power dissipation is also going to decrease. We'll see what those are. Okay, next integration, because of more integration, the manufacturing cost is going to decrease. Obviously, if you want to manufacture three ICs, three different ICs, and you're going to manufacture a single IC, obviously the cost of manufacture is going to decrease. And almost no manual assembly here. No manual assembly means we are not going to assemble the chips inside this IC, which performs the operation of multiplier, adder, subtractor. And suppose if you consider single IC as an arithmetic logic unit itself, or even it can be a microprocessor, okay, your i3, i5, i7, i9, which is going to have the billions of transistors will be present on the IC. Okay, billions, remember, tens of billions of ICs are there in 2016 itself. Now it is around 114 billion transistor in an IC. Mass, it's a big number. Okay, 2016 it is around tens of billions. So number of transistors very high. Okay, next we'll see next slide. So how that is evaluation, how the ICs are evaluated with the years. Okay, I'll tell you here. This you can see here 1970s, and it is called as small scale integration. Next, in 80s, when it comes or end of 70s, it entered to medium scale integration. Then it is end of 80s, early 90s, it is large scale integration, beyond large scale integration. In 1990s or end of almost 80s, it's a very large scale integration came into picture. Okay, early 70s it is SSI, small scale integration. You can see here 1 to 10 logic gates used to be there. 1 to 10 logic gates on a single IC. One logic gate, and one logic gate it is going to required. If you have a NAND gate, NOR gate, it depends which logic gate it is required. So you're going to have 4 transistors and for a single logic gate. We'll see how you're going to tell that for NAND gate you required 4 transistors, for OR gate it will be more transistor. This we'll see. And flip flop, then we have counters here in the medium scale integration. So the number of transistors which are going to be there in early 70s are around 10 to 40 transistors, or 1 to 40 transistors. That is very small number. You can see 1 to 10 also, it depends how the design was made. Okay, 1 to 40 number of transistors you can say, because here it is 10. Each logic gate required to have 4 transistors, 2 transistors, depends on the logic gate. So the number of transistors are very small in case of small scale integration. Now next, it is the era of medium scale integration, end of 70s, something like that. So you have counters. You know, we have studied in logic, I mean DLD, subdigital logic design, or whatever the subject you have studied. There you have studied about counters, which require the number of flip-flops to implement the counters. Okay, so flip-flops are used to implement the counters, and each flip-flop consists of logic gates, NOR gates, NAND gates, like that. Okay, so if you want to have a flip-flop, you require to have number of logic gates. If you use NOR gates, again you know that latch 2 NOR gates are 2 NAND gates. If you go for master slave, more number of logic gates required. Each logic gate, suppose a 4 transistors, 2 logic gates means 8 number of transistors. If you have one flip flop means 4 NAND gates. Some more circuitry is required. 4 into 4, 16 transistors are required for a flip flop. Now for a counter you are going to require more number of flip flops. Suppose 4 number of flip flops required to implement one counter. Suppose 4 into 16, it increased to 64 transistor. Okay, like that, number, the size of the counter increases, number of transistors are going to increase. So medium scale integration, it can be 40 to 400 number of transistors only. 40 to 400, 10 to 100, 10 to, okay. Then next it is comes to the large scale integration, where it jumps into thousands, okay. Thousands, below 20,000, around 10,000, depends on which IC you are implementing, okay. So microprocessor, that is early microprocessor, not like i3, i4, i5, i7. This is very old type microprocessor, where you have small calculations only can be performed. So there you're going to have thousands of transistors will be there. Next, coming to, you have here very large scale integration. Here the jump it is taken in very large scale integration. You have around lakhs, starting with 1 lakh, 3 lakh, then millions of transistors, then crores. Now it is in billions, okay. Now even it is said to be very large scale integration only. Some people have given the name, when it enter into millions of transistors, they have given ultra large scale integration. Then further it was increased, they have given giant large scale integration, GLSI. So whatever the names now, not ULSI, not GLSI, only all the billions of transistors whichever we have, it comes under very large scale integration, okay. Even 64-bit microprocessor, cache memory, floating point, arithmetic units, all comes into picture here, okay. That is very large scale integration, from lakhs of transistors, millions of transistors, enter into billions, tens of billions, now around 100, 114 billion transistors also. It is given the name as very large scale integration only, okay. So this is an evaluation with respect to sizes. Next we have evaluation with respect to the type of technology it is used. Here bipolar technology, where you're going to have uh, BJTs are going to be there, and fabrication of bipolar IC it used to be there, okay. Bipolar IC, you know that bipolar transistor, it is going to be, suppose NPN you have or PNP you have, okay. Combination of these two you can have, it depends on the circuit which you're going to divide design, okay. And even you're going to have the resistors, you're going to have required the capacitors, all these NPN transistor, PNP resistors, you can design with the bipolar technology, okay. It is little tough to have the capacitors, resistors with the bipolar technology. Using MOS we'll see, that is easy, but the area occupied is going to be very large, that we'll see within some minutes of time. So bipolar technology, it used to be there. Then we have this transistor logic also, you can say. Then emitter coupled logic, this also you can say that it is bipolar technology, where you transistor logic means BJTs are used. Bipolar technology, why I am saying is, the fabrication of this NPN PNP used to be done using the bipolar technology, where they used to have, I think you know, this is NPN, okay. Here if you remember, this NPN is only for this transistor, okay. If you change the arrow direction here, then it is going to be PNP, okay. So how this we got NPN, you have remember, you have studied already in basic electronics, semiconductor electronics, that pure semiconductor you have, it is called as intrinsic semiconductor. Then if you add the impurities to this pure semiconductor, you're going to get P type or N type semiconductor. That is, if you have pure semiconductor, that is Si, or it can be germanium. Mostly silicon is used in fabrication of ICs. The melting point is higher for silicon than germanium. It has some good properties when compared to germanium. So silicon, the purest it is going to be, it is used, that is intrinsic semiconductor is called. Now if you dope this pure silicon with trivalent gas, then we get it as boron. Trivalent gas is boron. If you dope the pure silicon with boron, you get it as p type semiconductor. Suppose if you dope the pure semiconductor with phosphorus, that is pentavalent, 5 electrons are there, valence electrons, so that if you dope with phosphorus, then we get from pure silicon to n type. More number of impurity atoms you add, then n to n plus we get. Okay, and if you increase the timing of doping, initially it is n minus, then n, further increase the time of doping, increase the concentration, then it becomes as n plus, p minus, p plus, like this also. If you increase the impurities by increasing the time of doping, the concentration n minus, then n plus. Similarly for p minus, p to p plus. Okay, so like how the fabrication used to be done in bipolar technology, but it occupies larger area. Bipolar has its problems. So then it is transistor logic also you have studied in linear integrated circuit, I think LICA like subjects, where you are going to have using transistors you can implement AND gates, NAND gates, NOR gates, using only bipolar transistors, that is fabricated, but it occupies a larger area and it has some problems, input impedance problem like this. Then you have this one, that is emitter coupled logic, ECL. I'll just ECL logic you have, that is this also I think you have studied already. Emitters of the two transistor used to be connected, and further logic it used to be there, using which you can have the gate circuits, emitter coupled logic. Next, the most important era, when actually metal oxide MOS transistors were invented, you can invented before, okay, invented before the bipolar technology itself, but because of the fabrication difficulties at that time of 1950s, MOS transistors were not popular, but now the fabrication has very, it is complicated, but the tools and the machinery is available, so that's why MOS has become very popular. MOS transistors and MOS technology has become very popular, and NMOS, PMOS, it was came into now fabrication. Okay, combination of NMOS, PMOS, it gives CMOS. That also we'll see in coming slides possible or in the next classes. Okay, MOS IC was cheaper than bipolar IC and led to investment and growth. Obviously, everything it is the marketing. Who are going to invest the money, they will see which is cheaper and which design you get in less price. So MOS IC was cheaper than bipolar IC. Okay, so that's why investments are grown in MOS market. So here first we have IC evaluation with respect to the number of transistor, number of gates, SSI, MSI, LSI. Okay, then very large scale integration. Then we have again in the second part of IC evaluation with respect to bipolar technology and mostly MOS technology, and the number of MOS transistor which can be fabricated in IC are going to be very large. That's why denser, denser means more number of transistors in small area, so denser it make and less power is consumed than it compared to the bipolar ICs. Because okay, that's why MOS transistors were popular nowadays. That right. Next we have another evaluation related to the material which is used. Okay, here we can have it is given, actually I'll write what is MOS. It is already written earlier in the slide. MOS is nothing but metal oxide semiconductor. What is MOS? It is metal oxide and semiconductor. It is MOS. Now here they have given, I'll tell you what is this. Aluminum gate is replaced with polysilicon by early 1980s. It was because of contact problems and short circuit problem, this metal which used to be there in place of polysilicon earlier, that metal is aluminum metal is replaced by polysilicon. Polysilicon is crystalline silicon, densely packed crystals of silicon is called as polysilicon. The properties are near to the metal. So that aluminum gate is replaced with polysilicon. Closely packed crystals of silicon is used in place of aluminum gate. Okay, now that is metal oxide semiconductor, but this metal is replaced with polysilicon. So the name they have not changed it as POS, still it is called as MOS only. Even aluminum gates are replaced with polysilicon. Also the name it is metal oxide semiconductor. M is metal, O is oxide, and semiconductor. Why the name it came, I'll tell you here. I think you studied this, how the NMOS transistor it used to be there. NMOS, I'll just draw, don't worry, in detail we'll see about this later classes. This is P substrate. I just want to tell you why the name MOS came here, metal oxide semiconductor. Here you have this slash lines represents the gate. Earlier it used to be, this one used to be metal, now it is nothing but polysilicon. This dotted lines here you have silicon dioxide, which is nothing but SiO2, silicon dioxide, and this is complete, it is P substrate. Here everything it is P substrate. So earlier in place of poly you used to have metal, then you have oxide, then you have the P substrate. So that's why the name it came metal oxide and semiconductor. Okay, right. Now we'll see little detail about this. CMOS, it is combination of N channel and P channel. That's now what I have drawn is NMOS, and if you replace N plus with P plus and P substrate with N substrate, then we get it as PMOS. So complementary MOS is a combination of NMOS and PMOS. Okay, this IC evaluation here it is, earlier the gates used to be implemented only using NMOS transit. This is the symbol of NMOS. Okay, using only NMOS transistor, gates used to be designed. Next, the CMOS came into picture, where the combination of NMOS, that is N channel MOS, and PMOS it was introduced. CMOS, combination of N channel MOS and P channel MOS gives complementary CMOS. NMOS, the name it came because the channel which used to be present, we'll see this, don't worry. Here the channel used to be there, this is the channel which I am darkening, that is of N type, then it is called as NMOS. If this channel is of P type with holes, then it is PMOS. N type means with electrons. Okay, right. So MOS transistor gives low power consumption, simplified fabrication process when compared to bipolar. So this everything it is with respect to MOS only. Advantages of CMOS you can say are MOS transistor fabrication, low power consumption, the required power supply it is going to be less when compared to the bipolar. I'll tell here, in bipolar technology it used to have around 10 volts, 12 volts, 15 volts of power supply, very old. Next 12 volts, then 10 volts. Even some bipolar technology or TTL, this required can be even 5 volts. But this CMOS or MOS technology can work even on 1.2 volts or less than 1.2, 1 volt, it depends on the design. So the required power consumption, voltage is decrease means power consumption required is going to decrease. Okay, that is what power consumption is lower. Simplified fabrication process when compared to the bipolar, that also we'll see later classes. Next we have bi CMOS. After CMOS even you have By CMOS type logic, it is by CMOS logic, where it is by CMOS, basically it is a combination of BJT plus CMOS. By here it is combination of BJT and it is CMOS, that is called as by CMOS. The problem with CMOS is it can't drive larger loads, whereas BJT can drive larger loads, more gain it will provide when compared to CMOS. Larger loads can be driven by BJT, bipolar technology, when compared to CMOS, because size of CMOS is very small. That's why it can't provide more current when it can't drive larger loads, means that is the reason. BJTs can drive larger loads. So if you have the combination of BJT and CMOS, that can be called as by CMOS logic. But this by CMOS logic, this hybrid bipolar and CMOS for high speed, and at the, if you have an IC, the external pins you're going to have to an IC. Okay, external pins used to be there for the IC. At the intersection of the chip and the external pin, here you're going to have pads are going to be there for designing the pads which can drive our external uh, devices. By CMOS, by CMOS are used. The main here is it can drive larger loads and the speed also high. Next, it is given instead of silicon or germanium, mostly it is used silicon only, they went for gallium arsenide material instead of silicon. Here material itself changed, gallium arsenide material, to increase the speed of operation. It is gallium arsenide they have used. Material it is changed, of silicon it is gallium arsenide. Next, silicon germanium, it is heterogeneous, it is called, mostly preferred for radio frequency signal. You can have better result, they say, even for using CMOS amplifiers, that is PMOS and MOS combination also we can have the RF circuit designs. Okay, this silicon germanium hetero mean combination of that type of material also can be used to design the transistors. Okay, RF means at radio frequencies, right? Next, we'll see the speed power performance available in the present, that is we are going to compare all. Just now we have seen CMOS, and before the CMOS we have seen ECL. Okay, now we have seen by CMOS, NMOS, and now it comes to the gallium arsenide material. If you use to design the transistors itself, then what is the effect you are going to get? Now this figure, if you see, this compares the power dissipated per gate. That is, if you have, you know this, okay, NAND gate, you can take AND gate, NOR gate, whatever. Per gate means for one individual gate how much power it is dissipated, and what is the propagation delay, that is how much time it will take when you given the input to get the output, how much time it takes for the response to come. Once you given the input, how much time it takes to get the output, that is called as propagation delay, right? Power dissipation means how much power it dissipates. It is in milliwatts. Milli means 10 to the power of minus 3. This is milliwatts. Very small power dissipation means micro, that is 10 to the power of minus 6 watts. So that is also very much important. Here you have power dissipation is important, and delay should be in nanoseconds, less than that if possible. Even microseconds of delay is very big delay. Here nanoseconds of delay it is acceptable here, that's why it is, we'll see the comparison. So if you observe here, most you have here CMOS. If you observe the CMOS and if you draw a vertical line on the x-axis where we have taken power dissipation, okay, you have CMOS gives a power dissipation of around 100 microwatts, very small. Okay, when compared to milliwatts, it is 100 microwatts is very small. Right. And the delay, propagation delay, if you see, that's also best, that is in nanoseconds it is. Okay, I think you know that when pico means 10 to the power of minus 12, nano means 10 to the power of minus 9. Okay, if you observe here, with respect to gallium arsenide materials used, the power dissipation here is almost going to in milliwatts range. It depends on logic gate, number of gates increase. Okay, so you can see here the power dissipation is going to the range of milliwatts, whereas the starting it is okay, it is compatible with the CMOS, and the speed is also good because the delay is only in 100 picoseconds. 100 pico means how much? 10 to the power of minus 10. Okay, which is zero point 0.1 nano. I think you know this, zero point 0.1 nano, whereas CMOS is in nano, almost 10 times faster. That is, gallium arsenide is 10 times faster, but power dissipation, when you observe, it is 100 microwatts, but here it is entering into the range of milliwatts. So that's why mostly CMOS it is preferred. In some special cases like RF circuit design, where it is required to be very fast, designs are required, then gallium arsenide material is used to fabricate. Okay, right. Now others also will just compare here. With respect to NMOS is simple, you can, now if you come to the BiCMOS, it is near to the microwatts, hundreds of microwatts, but it is going up to 10 milliwatts, the range increased. Most important in CMOS is power dissipation is less here, and the speed also more. If you consider this point, speed is good and power dissipation also less. Okay, that's the mostly CMOS is used. BiCMOS special cases, gallium arsenide special cases. NMOS is now, NMOS technology means to implement a NAND gate, NOR gate, only NMOS transistors, no PMOS transistors used, then it is called as NMOS technology. If you use NMOS as well as PMOS transistors to design the gates, then if you have the combination, then it is called as CMOS technology. BiCMOS, just now I have told. ECL also have told, gallium arsenide material itself instead of silicon. Okay, so NMOS it is going to have delay is more, and the power dissipation it is in milliwatts range. So it depends now. Emitter coupled logic it is not used much now, almost not used. 10 milliwatts of power, and the delay if you see here, it is slower when compared to CMOS. So this is, we have the comparison between different types of technologies. Okay, power performance, speed, power performance of the available technologies. Now we'll see the important bipolar technology versus CMOS technology. Why bipolar was left and why CMOS was introduced, that is low. If you see the comparison, obviously here you have low static power dissipation, high power dissipation. In bipolar, power dissipation will be high, and in CMOS technology, static power dissipation is less. We'll see in detail when we see the circuit, then we understand about the low static power dissipation. Static means when we apply the DC inputs, it is going to be static power dissipation. Okay, next it comes to the input impedance. Okay, second point of comparison here, it is input impedance here. Why it is input impedance is very high. Okay, high input impedance, as the MOS technology which we use, silicon dioxide is, just now I have drawn, very fast I'll draw here. This is N plus, this is N plus. Here we have silicon dioxide, polysilicon P substrate. So here the dotted lines, dots, not lines, dots represent silicon dioxide, which is an insulator. So when we connect here the gate terminal, this is source and drain, we'll see in detail. So here the impedance is because of silicon dioxide. Obviously insulator gives very high input impedance, whereas coming to the bipolar technology, no silicon dioxide is present, so low input impedance it is going to have. So required current to drive the bipolar is going to be more high, whereas low drive current, smaller values of drive current, we can operate the MOS transistor, NMOS or PMOS. Now here scalable threshold voltage, I'll tell you what is threshold voltage. Is the minimum gate to source voltage required to on the transistor. Now you remember just some it is not exact definition of threshold voltage is defined as the minimum gate to source voltage required to form the channel, which is scalable. As the size of the NMOS or PMOS transistor is reduced, the threshold voltage is also going to be scaled. Okay, low voltage swing logic, the output swing, when we compare the logic 1 and logic 0, the swing logics are going to be low voltage swings. In case of bipolar technology, high noise margin noise margin, here it is. VDD logic 1, generally we can take it as 3 volts or 2.2 volts, it depends. Okay, and suppose roughly if you consider logic 1 as 5 volts, so up to 4 volts you can consider as logic 1 itself. Okay, and 0 volts it is logic 0, and even up to 1 volt or 1.4 volt, up to that also we can consider it as logic 0. Like that you're going to have the noise margin, it is high in case of MOS transistor. In detail we'll see in later classes. Most important here it is packaging density is very high, because the size of the MOS transistor is very small when compared to the size of the bipolar, IC form only it is. Okay, don't think that bipolar means what you have done experiments using the discrete components. Here it is bipolar technology is also IC form, CMOS technology also IC form, but to design, to fabricate bipolar transistors, the size of the silicon required is large, high, bigger sizes when compared to the MOS transistors. So on the same size square, 1 micrometer by 1 micrometer, if you take, more number of MOS transistors can be fabricated when compared to the bipolar technology. That is why CMOS technology means combination of NMOS and PMOS. So packaging density is high. Okay, high delay sensitive to load, fan out limitations, because that's now I have told the driving capability of CMOS technology is small, because the size is small, it can't drive larger loads. So number of output gates which we can drive with a gate designed with CMOS is less number of gates can be driven by a gate or by a circuit, because it cannot provide high larger currents, whereas bipolar gives low delay sensitive to load, because it is drive larger loads, it provides more current. Bigger size transistor bipolar, so it gives more current. Now you have low output drive current, as I told you, that's why fan out limitations are there. High output drive current, that's why it can drive larger loads, more current. GM transconductance, it is small and proportional to input voltage directly, so gain given by this MOS transistor less when compared to the bipolar transistor, where transconductance is proportional to exponential of the input voltage. Bidirectional capability, source drain can be interchangeable in case of MOS transistor. We will see source drain can be interchangeable. and here you have high ft at low current. Okay, that is frequencies related concept, we'll see later classes. Essential unidirectional, because in bipolar it can be because of electrons or it can be because of holes only. Okay, this bidirectional capability of MOS means source drain can be interchangeable. Here also it is because of holes NMOS transistor, or it is because of electrons it is NMOS transistor, because of holes it is PMOS, the channel which is found. And near ideal switch device, that is last it is having the CMOS technology. If you see, it is near ideal switching device. I'll show you. If you take NMOS transistor, this is the symbol of NMOS. Maybe you have studied in basic electronics. At the end, not you studied. Okay, this is NMOS symbol. Okay, where you have three terminals. Basically, it is going to have four terminal device. And PMOS, we have, this is bubble. If you add, then four terminal also it is going to be, then it is going to be PMOS. Okay, so here symbolically this arrow mark you can have PMOS. So nearly ideal switch means whenever we provide the gate voltage, sufficient gate voltage to NMOS or sufficient gate voltage to PMOS, it is going to be acts as an ideal switch. It is going to on and off very fast. Nearly ideal switching device. So NMOS on means it is acts as a closed switch. This is on. Okay, NMOS or PMOS, it can be NMOS or PMOS. It is on means it is a closed switch, and if it is off means it is open switch. Okay, off means it is going to act as open switch, off. So NMOS can be used as a switch, as well as PMOS also can be used as a switch, but these are ideal switching devices when we compare to the bipolar BJT transistors, which is bipolar technology. Okay, whenever we provide the sufficient gate voltage, this is gate, this is source, this is drain, and this for NMOS also, this is gate, this is source, this is drain. The fourth terminal is going to be bulk or body, and the PMOS also fourth terminal is going to be bulk or body, it is going to be. Okay, so this is about the comparison between CMOS and bipolar technology. Next we have VLSI design cycle. I'll just give very briefly and we'll stop for today. We'll continue this VLSI design cycle in the next lecture. So you have system specifications, architectural design, functional design. So these are about VLSI design cycle. That is, number of levels of design will be there. Whenever we want to design an IC, it can be a microprocessor or it can be a specific IC like digital signal processor or image processing IC you want. Okay, or FPGA want to design. There will be a design cycle for each IC. Okay, that will continue in the next class. Thank you for watching. We'll stop here.